Welcome back to the deep dive. So, last time, we really got into the foundations, didn't we?
We did. Data modeling fundamentals, those crucial ACID properties for keeping data reliable.
Yeah, and relational database design the conceptual, logical, physical stuff, building those solid, structured databases.
Exactly, laying the groundwork.
But, well, the data world didn't exactly stay static after that, did it? Things started moving fast.
Incredibly fast,
Yeah,
which, brought a whole new wave of challenges and naturally demanded new solutions.
absolutely. So today, we're jumping ahead. We need to talk about that evolution, that explosion. We're talking big data
Mhm.
and the arrival of something quite different, the data lake. We're going to explore how data architecture took a sharp turn away from those traditional methods we discussed.
Right. And that's our mission today, really, to unpack that shift.
Hmm.
Why did we move from traditional data warehouses to these modern data lakes?
Mhm.
What were the driving forces, the technologies behind it? It's a story of adapting to just, unprecedented amounts of data.
Okay, let's paint the picture then. Turn of the 21st century. Suddenly, you've got the internet booming, social media taking off, mobile phones everywhere.
Sensors, IoT devices.
Exactly. The Internet of Things, smart thermostats, factory sensors, data just pouring in from everywhere. It wasn't a trickle. It felt more like a fire hose.
It really did. A deluge.
And this flood of data, it had these key characteristics. People started talking about the three V's, volume, just sheer amounts of data.
Unbelievable amounts.
Variety. It wasn't just neat tables anymore, was it? Texts, images, logs, sensor readings, all sorts of formats.
Structured, semi-structured, completely unstructured,
Yeah.
all mixed together.
And velocity, the speed it was coming in at, real-time feeds, constant streams.
Right. So volume, variety, velocity. That combination, that's what really defined big data
Yeah.
and what started to really stress the existing systems.
Yeah, it created this huge bottleneck, didn't it? It kind of stifled innovation because people couldn't process the data fast enough.
Precisely. And that brings us to the core problem. Those traditional data warehouse systems, the ones built on those relational principles we discussed, they were just fundamentally not designed for this big data world. Their limitations became painfully obvious very quickly.
So let's dig into that a bit. To see why they struggled, we need to understand how they worked. You mentioned they operate on a principle called schema on write. What does that actually mean in practice?
Okay, yeah. Schema on write. It means the structure, the schema, had to be defined before any data could even enter the warehouse.
Ah,
So you had this very rigid process: extract, transform, load, ETL. You'd extract data from somewhere.
like an operational database or logs.
Right. Then you'd have to transform it, clean it, validate it, maybe aggregate it, basically force it to fit into a predefined structure, a specific schema you'd already designed.
And only then could you load it into the warehouse.
Exactly. Only him. And once inside, usually lived in very structured formats like star schemas or snowflake schemas.
Yeah.
You had dimension tables for descriptive things, fact tables for measurements. Very organized.
Which sounds great for clean reporting data.
It was excellent for that.
Yeah.
For standard business intelligence, asking predefined questions. But, and this is a big but.
Here come the limitations.
Right. First, these ETL processes and the warehouse design, they took a long time, months, sometimes years, and they were expensive
I can imagine. All that planning and processing up front.
and inflexible. If your business needs changed or a new data source popped up with a different format, adapting the schema and the ETL was a major undertaking, really slow.
Okay, time, cost, inflexibility. What else? Were there technical hurdles too with the big data characteristics?
Definitely. Tooling was one. You often needed specialized, quite expensive software, things like Informatica for ETL, Cognos, or MicroStrategy for reporting. And the hardware underneath had to be pretty robust, reliable, and usually costly.
So not cheap commodity hardware.
Not typically, no. But maybe the biggest hurdle was the data type restriction. They excelled at structured data rows and columns. But all that messy, semi-structured stuff like JSON or XML or the completely unstructured data images, video, plain text, they really choked on that.
Which was exactly the kind of data that was exploding with big data.
Precisely. And finally, the purpose. They were built for OLAP online analytical processing. Great for summarized reports answering known questions. But for exploratory analysis, data science, machine learning, where you often need the raw, messy, untransformed data to find new patterns, not so good. They weren't designed for that kind of work.
So it really sounds like a perfect storm of limitations hitting this massive wave of new data.
That's a good way to put it. The fundamental reason for the shift we're talking about is that organizations desperately needed something more flexible, something that could scale out more easily and cost effectively, and something that could handle all this data, not just the neat structured parts. The old model just wasn't cutting it anymore.
That inflexibility really opened the door for new ideas. And you mentioned things started to change conceptually. Google played a role.
Yes, absolutely. Around 2003, Google published a research paper on something called the Google File System, GFS. It wasn't widely known outside certain circles then, but it laid out core ideas for managing huge data sets across clusters of ordinary computers. Distributed computing concepts.
So moving away from single powerful machines.
Exactly. And building on those ideas, the open source community developed Apache Hadoop. Hadoop basically took those concepts and provided a practical framework. Suddenly, you could store and process massive data sets using clusters of relatively cheap commodity hardware.
That sounds like a game changer for cost and scale.
It was huge. It sort of democratized large-scale data processing. It wasn't just for the Googles anymore.
And alongside Hadoop, another piece of technology really accelerated this whole data lake idea, especially in the cloud era, Amazon S3. How did S3 fit in?
S3, Amazon's simple storage service, was pivotal. Its impact was massive for several reasons. One, incredible scalability. You could store virtually unlimited amounts of data.
Right?
Two, cost effectiveness. You basically pay only for what you store and access, which is very different from buying and managing large, dedicated hardware clusters.
Much more efficient.
Much more. Plus, it offered high durability and availability. But crucially, S3 allowed you to decouple storage from compute.
What does that mean, decoupling?
Your storage layer, S3, is separate from the processing layer, like maybe an EC2 cluster running Spark or Hadoop. You can scale them independently. Need more storage, just add it to S3. Need more processing power for a short time. Spin up a bigger compute cluster, run your job, and shut it down. You're not paying for idle compute just to keep data stored.
Okay. That flexibility sounds incredibly powerful compared to the old integrated warehouse systems.
It's a fundamental architectural difference.
Yeah.
And it leads us right to the core idea of the data lake.
Okay, so what is a data lake, fundamentally?
Think of it as a central repository, a place where you can store all your data structured, semi-structured, unstructured from various sources, but crucially, you store it in its raw native format.
Raw. So no upfront transformation like in the ETL process.
Exactly. No predefined schema is imposed when the data lands in the lake. You just pour it all in, like a real lake collecting water from different rivers. You collect data from different sources.
Okay, so if there's no schema when you write the data in, how do you actually use it?
That's the other key principle. Schema on read.
Schema on read, the opposite of the warehouse's schema on write.
Precisely. The structure, the schema, is applied only when you read or query the data for a specific purpose. So a data scientist might apply one schema for an exploratory analysis, while a BI tool might apply a different, more structured schema for a dashboard using the same underlying raw data.
Wow, okay. That sounds incredibly flexible. You're not locked into one structure up front.
Exactly. That's the core benefit. It provides immense flexibility. You store the data once in its raw form, and then multiple users or applications can interpret it differently as needed. This massively speeds up the process of getting data in and makes it much easier to adapt to new types of analysis or new data sources later.
So what are the big advantages then, summing up these modern data lakes?
Well, cost effectiveness is huge, especially using cloud storage like S3, Azure Blob Storage, or Google Cloud Storage. They provide robust support for all kinds of advanced analytics, data science, machine learning, model training, because you have that raw data available.
Right, which those disciplines really need.
They do, and the ability to scale storage and compute independently gives you incredible agility and efficiency. You're not over-provisioning expensive hardware.
So these lakes become central hubs for everything, regardless of format, keeping it all raw and ready.
That's the idea, a single source of truth for all data in its original state.
Now, you mentioned data coming from various sources. Often, especially for modern applications generating semi-structured data, we hear about NoSQL databases. How do they fit into this picture? Are they part of the data lake?
That's a great question. They play a distinct but very important complementary role. NoSQL databases are typically used as operational databases,
Operational, meaning?
meaning they often power the actual applications that generate the data. They're the transactional backbone. Think of online applications needing to read and write data very quickly, often for user interactions.
Okay, so they're handling the live application traffic.
Exactly. Examples might be column family stores like Cassandra or ScyllaDB, which are good when you have lots of writes and need to distribute data, or key value stores like DynamoDB, which are super fast for simple lookups. They're optimized for high throughput, low latency operational tasks.
So they're producing the data that might end up in the data lake.
Precisely. They are often a key source system feeding data into the data lake, but their primary job is different. Data lakes, and to some extent, data warehouses, are optimized for analytical workloads, OLAP, running complex queries over large historical data sets, batch processing, training ML models.
So operational speed versus analytical depth.
That's a good way to think about it.
Yeah.
NoSQL for the fast, transactional side, data lakes for the broad, deep, analytical side, handling historical data at scale. They serve different but equally critical functions in a modern data stack.
Right. Okay, this has been a fascinating journey today. We've really seen the pressures that big data put on traditional systems and how that drove the need for a completely new approach, leading us to the data lake concept.
Yeah, we've covered the limitations of schema